All right, well, welcome to the afternoon session. The next speaker is first time here, but a member of his committee has been here 30 times, but is unfortunately unable to make it this year to the mini conference, Charlie Suttle. So, Michael Yatauro, connections between stability theorems and best monotone theorems in graph theory.
Yes. Thank you for coming. Thank you to the organizers for inviting me. Speaking of Charlie Suffel, he has always mentioned this conference fondly, and I personally have always been meaning to make it out here, so it was a pleasure to be invited and finally able to attend. It's a shame that he himself wasn't able to be here, but hopefully I'll be finding some time once I'm back in Jersey to go up and visit him over at Stevens, because I know he's back to teaching. He's hanging in there. He's doing well. Okay, so yeah, so I come from Penn State Brandywine. It's a campus right outside of Philadelphia, affiliated with Penn State, but I did my graduate work at Stevens, so I know Charlie Suffel. I worked directly with Douglas Bauer on my thesis, and best monotone theorems were a big part of my thesis. And this research kind of brought me full circle because now I've been looking into these so-called stability theorems, and we started to realize that there were these connections and there were similarities. So I wanted to explore those similarities and connections and then also look at the history and then some of the more recent results and see how those ideas translate to what's been done in recent years. So we're just going to consider finite simple graphs. And anytime we have a graph property, we're going to be considering increasing graph properties, those for which adding an edge preserves the property. Hamiltonicity, connectivity are such properties. So a degree of a vertex, denoted d of u, is the number of vertices adjacent to it. So here in this example, we have the individual degrees of the 5 vertices indicated, how many other vertices are adjacent to it. So these are just some preliminaries. We're going to talk first of all on Hamiltonicity. So if you're familiar with graph structures and graph properties, in a graph, we can have what's called a cycle, where you essentially start at a vertex and you transition along edges, never reusing a vertex until you come back to where you started. And that's a cycle. It's Hamiltonian if you can use all of the vertices in that manner and come back to where you started, otherwise non-Hamiltonian. So here are 2 examples, one of which on the left is Hamiltonian. You can traverse the graph from starting vertex back using all the vertices only once until you come back, but you can't do so on the right, which is a so-called bow tie graph. No matter where you start in the graph, you're always going to get stuck at that middle vertex and have to use it more than once on your way back. Okay, so what is stability? Well, stability for a property is assigning an integer associated with that graph property. And here's the definition from 1976. A property P is k-stable if whenever G plus an edge has the property P and the vertices that make that edge, the sum of their degrees is at least k, then G itself has property P. So if U and V are already adjacent in G, then G plus UV is the same graph. So we're going to primarily consider graphs where the edge UV is present in G plus UV, but not adjacent vertices in G itself. So, for example, in Hamiltonicity, if you add an edge, you expect to preserve Hamiltonicity, but if you remove an edge, you don't expect to preserve Hamiltonicity, okay? But these pairs would preserve the Hamiltonicity property. So the stability of that property, denoted S of P, it's the smallest such P for which you have the graph, or which you have the property be k-stable. Okay, so this was all prompted by a well-known result of OR, where any non-adjacent vertices, if you take the sum of their degrees, if it's at least n, then the graph is Hamiltonian if that's true for all pairs of non-adjacent vertices, U and V. But along the way, he actually proved that it was an n-stable property, that Hamiltonicity had this associated property where if you add this edge, and the sum of the degrees happen to be at least n, well, if that graph was Hamiltonian, then the graph you started with was Hamiltonian as well. Okay? So they then looked at, well, okay, so we have this notion of stability, so they created what's called a K-closure of a graph. So this is not relative to the property itself. So what they're doing is they're taking the graph itself and they're recursively adding edges between pairs of vertices for which so they're not already adjacent and the degree sum is at least n, and they're adding these pairs of vertices, they're adding edges between them. And it doesn't matter in which sequence you carry out this addition of edges, you always end up with the same graph called the closure. So it's unique regardless of the sequence of added edges. And of course, once you get to the closure, all the remaining non-adjacent edges in the closure graph all have degree sum less than k, because otherwise you would have added the edge between them. Okay, so a proposition that followed was that if, now we're bringing the property back, if the property is k-stable and the closure has that property, then the graph itself has that property. So we would just work backwards to the original graph G, preserving the property P along the way. Okay? And an example, G is Hamiltonian if and only if the closure C sub n is Hamiltonian. And it just so happens that when this works, C sub n is always a complete graph. We'll see that in a bit. But here's an example of a sixth closure for a particular graph. So inside each vertex is the degree. So what we're going to do is we're going to look for pairs of vertices that are non-adjacent for which the degree sum is at least 6. And in this case, that's the n value, the number of vertices. So U and V indicated here, we add an edge. Then we have this new pair U and V, which we can then go about adding the edge because the sum of degrees is 6. And then we have this new pair of U and V, add that. And at this point, all the remaining non-adjacent pairs all have degree sum less than 6. So we would stop here. So this gives us the sixth closure. And what we can see is we can tell that not only is the sixth closure non-Hamiltonian, but the original graph we started with was non-Hamiltonian as well. So that should be the case if we're taking C sub 6, where 6 is the number of vertices. Okay, so that's a demonstration of when a property is stable, in this case n stable for Hamiltonicity, and a closure. So now we're going to transition into what are known as best monotone degree sequence theorems. So a degree sequence is a list of the individual degrees of the vertices. So you get repetition if multiple vertices have the same degree. And we're going to be denoting degree sequences of a graph G by pi of G. And we will also be listing them in non-decreasing order. Okay, so either equal or up as we go along. Okay, so here's an example of a graph. Its individual degrees are indicated, and then we list them out in non-decreasing order. We have a shorthand notation. If a specific degree appears more than once, we give that degree an exponent as to its multiplicity, how many times it appears. Okay, so what we'd like to then do is talk about, well, how can we use a degree sequence to identify if a graph has a certain property? So a theorem which uses conditions on the degree sequence of a graph to determine if it has a property, we're going to call those degree condition theorems for P. So here is a classic example by Kvatel where if the graph's degree sequence satisfies the conditions indicated, so each condition is stated as an implication, and there are roughly n over 2 such implications that have to be true. If they are all true, then the graph itself is Hamiltonian, okay? It actually says more in that every realization of that specific degree sequence is Hamiltonian. Okay, but if we're just talking about a single graph and it meets those conditions, the graph is Hamiltonian. So here's an example where n equals 5, so 5 is the number of vertices. So this is what the implications would look like. So I counts in this case just 1 and 2. And then you check the individual instances of those implications. So if we take this particular graph, it's clearly Hamiltonian. Here's its degree sequence, 2, 2, 3, 3, 4. So D1 less than or equal to 1 implies D4 greater than or equal to 4. When I equals 1, that's satisfied vacuously because D1 is 2. And then D2 less than or equal to 2 does in fact imply D3 bigger than or equal to 3 because D3 is 3. So this particular graph satisfies the degree conditions of Quattel's theorem, and it is Hamiltonian, okay? Now, this may be a sufficient condition, but it's not necessary. There are graphs for which the graph is Hamiltonian, but its degree sequence fails the conditions of Quattel's theorem, okay? So we're going to look at specific properties and generalize those properties that this degree theorem happens to possess. So the first of which is a non-traditional definition of majorization. In fact, when I was working with Doug Bauer, I was relatively new to the field and I didn't know that there was another accepted terminology and definition of majorization. But this is the one that I became familiar with. And it's simply looking at two sequences of the same length, and one majorizes the other if it's term by term greater than or equal to in every entry. So here's an example. This 3 2s and 2 3s majorizes all 2s because every entry is greater than or equal to 1 by 1. So a degree condition theorem, P, is monotone increasing if whenever the conditions of a degree sequence happen to be satisfied. So if a degree sequence satisfies the conditions of that theorem, then every majorizing degree sequence will also satisfy the conditions of that theorem, okay? So that means that if you take a degree sequence and it meets the conditions, and then you take a majorizing degree sequence, it's guaranteed to meet the conditions as well. That's what we call monotone increasing, or simply monotone. Okay, so that's one relevant property that Quattel's theorem has. It is a monotone increasing theorem. Another property is, well, here on this slide, we're defining two forms of optimality. One, Quattel's theorem, the first one here, does not have, but the second one it does. Optimal means, in a sense, that it would be a necessary condition. So if the conditions are met, then your graph has that property. So it would be optimal if the conditions aren't met, then your graph doesn't have that property. But that's not true of Quattel's theorem. But Quattel's theorem is what we call weakly optimal, in that if a degree sequence, pi of g, fails the conditions for that property, then there exists a graph g prime with a majorizing sequence that does not have that property, okay? So the graph itself, G, might have that property, but we're guaranteed to find a graph whose degree sequence majorizes the degree sequence of G, and it does not have that property, okay? That's called weak optimality. And Quattel's theorem is not optimal, but it is weakly optimal. And this is probably one of the only proofs that I decided to include, is that Quattel's theorem is weakly optimal. So the idea is if you fail Quattel's conditions, then what we wind up with is for some I, you end up saying that di is less than or equal to I, and the associated, here in this case, the consequent is false, so you have dn minus I less than or equal to n minus I minus 1. So the idea is build the largest sequence that you can think of that would be degrees for vertices and matches those conditions. Well, what we could do is we could just make the first I equal to I, and then the next n minus 2I until you stop at the location n minus I. So you, at I, up until that moment, your degrees are I. And then in order to get to n minus I, you have to go another n minus 2I locations. Make those as big as they can be. But those are less than or equal to n minus I minus 1. And then at that moment on, there are no restrictions, and you just make the degrees as big as you can, which would be for complete vertices adjacent to everything but themselves. you have n minus I. So the remaining n minus 1, are the degrees. So that would be the largest possible degree sequence you could achieve, term by term, and that would majorize pi. And its construction is indicated here, where k sub an integer is a complete graph on that many vertices. And then we have here, plus is the notation that I traditionally use for a complete join. So all possible edges going from one part of the graph up until the other part. So here we have a complete graph on I vertices, completely joined to I independent vertices, and then disjoint union with another complete graph or a clique. So this graph is guaranteed to be non-Hamiltonian. No matter where you start, you're going to get stuck at the bottom or in a component before you can come back. Another observation is that it's not one tough, if you're familiar with toughness, and every Hamiltonian graph is one tough. Okay. So the reason why we use the terminology best monotone, well, best, we're going to see in a moment. Monotone is because if the theorem has monotonicity, we call it a monotone theorem. So let's say T naught is a degree condition theorem for P. It is best monotone if it is monotone and weakly optimal. So what we find is that, I won't show the proof, but if you combine monotonicity and weak optimality, the following is a direct result. If T is any other monotone degree condition theorem for P, if a degree sequence pi satisfies the conditions of T, then pi will also satisfy the conditions of T naught. So the best monotone degree condition theorem will cast a larger net and classify more graphs as being that property or having that property than any other monotone condition for that property. Okay, so the set of graphs that T, which is not best monotone, declares as having property P is a subset of those that T naught declares as having property P. Okay, so as far as monotone degree condition theorems go, this one is best in a certain sense, is that it captures the most as classifying them as having that property. Okay, and Quattle's is best monotone. So that's the story behind, having a property be k-stable and then what we call a best monotone degree theorem. So in Bondi and Quattle's paper, A Method in Graph Theory, they demonstrate that when you know k-stability of a property, you can actually prove these individual, well, actually, this is just for a fixed k. K doesn't even have to be a stability value for a property. So this is outside the context of a property. If you just fix these numbers k, n, and t as positive integers, satisfying these individual properties, if G is G is a graph with a degree sequence, and there's no non-negative integer I where these inequalities are all satisfied, then the K closure has at least T vertices of degree n minus 1. So what we're going to find is that it's possible to extract from this statement degree theorems, monotone degree theorems for certain properties. And the idea is, can we write down best monotone degree theorems from these properties or conditions? So one observation is that if you assume the second item in that list of inequalities is true, but then imply that when that's true, the third item has to be false, okay, then T can be anything, including T equals n minus 1. Now, they cap T at n minus 1, but there's only one finite simple graph that can have at least n minus 1 complete vertices, and that's the complete graph, right? Because you say n minus 1 of them are adjacent to all other vertices, that means they're all adjacent to that other one that's still left that may not be included in that list. So that means every single vertex will have degree n minus 1. So you're looking at a complete graph. Okay, so That is a monotone condition to imply that the closure is complete. So now we're going to mix in some properties with that. So here's a corollary to that. So let k and n be positive integers. Okay, same restriction on k. So this is actually just a corollary that's restating that observation or note on the previous slide. So let G be a graph with this degree sequence. If for all I in that indicated range, you impose those implications, then your closure, your k closure, is guaranteed to be a complete graph. Okay, so if you set P equal to Hamiltonian and K equal to N, which is the stability of Hamiltonicity, you get the following. So let G be a graph with degree sequence indicated, D1 through Dn. If for all I in that range, but now we're setting K equal to N, so now you have the range of I values that you see in Kvattel's theorem as well. If we have the same implications as Kvattel's theorem, then the N closure will be complete. So if we look at these conditions, they're the same as Kvattel's theorem. So these conditions tell us that the graph is Hamiltonian, and they also tell us that the N closure is complete. So with that in mind, that sort of gives us the sense that this statement about the closure being complete, implying the graph is Hamiltonian, could be stronger than a best monotone theorem for Hamiltonicity. So here we see that if the complete closure or the N closure is complete, then if N is at least 3, your graph is definitely Hamiltonian. So if your closure is Hamiltonian, the original graph is Hamiltonian, so that holds true. But also, if the degree sequence satisfies the conditions of Kvattel's theorem, then you have that the N closure is complete. So the query would be, well, if the N closure is complete, then can you go the other way and say that the degree sequence must satisfy the conditions of Kvattel's theorem? Well, they have an example, Bondi and Kvattel produced this as a counterexample, where the N closure, or 6 closure, is K6, but it fails the conditions of Kvattel's theorem. So in that sense, Kvattel's theorem, it's not casting a larger net than this statement that if the closure is complete, your graph is Hamiltonian. It's missing some, okay? So the condition that if the closure is complete, your graph is Hamiltonian is stronger than just having the conditions of Kvattel's theorem. Okay, Kvattel's theorem can miss some that this theorem will catch as being Hamiltonian. So if we continue to explore more properties and ask, well, is it always the case that knowing a closure result, knowing that the closure is something implies the property? If that's one theorem and you have the best monotone theorem, is one always better than the other? Does one always cast a larger net than the other? And it seems from here that it would say that, well, a statement about the closure and its appearance implying a condition would cast a larger net and be stronger than the best monotone theorem. So here's another example. So another degree condition from this list that you can construct is, if instead you take the same range of I and assume, again, the second inequality is true, but now we're going to block the fourth inequality, okay? So if we block the fourth inequality, then that means that these are not all true statements. Then Ck of G has at least t vertices of degree n minus 1. So we can build that as an additional corollary, which is, again, a monotone condition, but this time it's not saying that the closure is complete. It's saying that the closure has at least t vertices of degree n minus 1. So it's telling us at least how many complete vertices there are. Okay? So for the next statement where we're going to look at connectivity, let P be a graph property and define this new function T of P and N to be the smallest number such that every graph of order n with at least T, P, N vertices of degree n minus 1 has property P. Okay, that's a mouthful. basically what it's saying is that this is the smallest number of complete vertices that guarantees the property P. Okay? So what we can look at then is this can transition into a theorem about G having the property P if you fix K to be the stability of P, T, I'm sorry, to be this T of Pn, the smallest number of complete vertices needed so that you're guaranteed to have that property P. And then you impose these conditions, so then the CK closure, so the closure C sub K, will have at least T vertices of degree n minus 1, but by the definition of T, G has property P. So this would also imply G has property P by fixing the appropriate T for that property. So here's an example where this corollary with resulting theorem gives us a familiar best monotone theorem. So let's let P equal S connected. I didn't use K connected because K is already in place. So the number of vertices whose removal disconnects the graph is at least S. Okay? You need at least that many to remove and disconnect the graph. So Bondi and Kvatel showed that the stability was this, the T value was this, and then you plug those into the previous theorem that was derived from the corollary, and these implications we get are best monotone relative to the property S connected. And Bondi knew of this theorem, it was already devised, and it is monotone and weakly optimal. So if that's true, then that means that we have here the closure was able to tell us something relevant about whether or not G has the property. And then we were able to also extract a best monotone theorem relative to that. So examples exist where the K closure has at least S vertices of degree n minus 1, but the best monotone degree conditions fail. So again, a statement about knowing something relevant to the closure. In this case, it has at least S many complete vertices. So this one is saying if your K closure, where K is n plus S minus 2, if that closure has at least S vertices that are complete, then your graph is S connected. That statement using a closure, that casts a larger net than the best monotone degree theorem for S connected. So here is another example where a related statement about the closure was stronger than the best monotone theorem for guaranteeing that property. So the generalization would be, so P is a graph property with a given stability and a given T value. So we're going to define n of P to be the smallest integer such that the complete graph with at least that many vertices has that property. Okay, so however many vertices you need in order to guarantee that the complete graph with that many vertices has the property. So here's a theorem. Let G be a graph on n at least n of P vertices. If either the K closure is K sub n, or the K closure has at least T vertices of degree n minus 1, then G has property P. Okay, because we've defined K in this case to be the stability of P, and T to be that T value where that number of complete vertices guarantees the property P. So this theorem is what we might call a closure theorem. So if you look at the closure and the closure has a certain property, then your graph has that property. So here's the query. If T is a best monotone degree condition theorem for P, and pi of G satisfies the conditions of T, must G also satisfy a closure condition that would guarantee the property P of one of those two types, either being complete or having the right number of vertices, that T value or more, that are complete. So in other words, are the closure conditions stronger than the conditions of the best monotone theorem? So These two examples seem to point to yes. Now, I started looking into more recent best monotone theorems and more recent results in stability and started to find things that were contrary to this. So let's look at the property of toughness. So toughness of a graph is you take the minimum by looking at all ratios formed by taking vertex cut sets, you look at the number of vertices and divide by the number of components remaining in the induced subgraph G minus X. Okay, so you take those vertices out, you have components, you have a certain number of them. Take all those ratios by looking at all cut sets and assign the smallest one. That's your toughness. So a graph is what we call C-tough is if its toughness is at least C. Okay, for the purpose of this talk, we are defining the toughness of a complete graph to be n minus 1. Sometimes it's defined to be infinity. But here's an example of a graph with toughness 1. The bottom two vertices are a cut set, and when you remove them, that's going to give you the smallest such ratio, 2 over 2. So this graph has toughness 1. Okay, so what are the results on stability, the t-value, and also best monotone theorems for C-tough? Well, here's the stability by Nate Kale. Now, this result, I put approximately 2012 because it was communicated verbally but never officially published. But it's proven and it's known. So here is what you need in order for the stability of C-tough. Here's the t-value. You need at least that many complete vertices to imply the graph is C-tough. And then here are best monotone degree conditions. So this one was back in 2009, but it gives us a collection of implications, and we check those implications for the corresponding range of I values. If they're all true, then the graph is C-tough. When C equals 1, it's actually Quattel's theorem, okay? Because even though Hamiltonicity implies one tough actually doesn't imply Hamiltonicity. Yeah. In fact, due to work by Doug Bauer, Ed Schmeichel, not even too tough right now. So they're trying to still identify, is there a lower bound on toughness that guarantees Hamiltonicity? That's still an open conjecture. Okay. So closure, in fact, is not stronger than best monotone, and vice versa. But I'm just going to do a quick run through here here are some counterexample graphs that I picked up, and they're very easy to construct. It's just you take a clique, and then you complete join it to an isolated singleton and another clique. And then one of the two vertices you're going to identify is that singleton up top that you're joining to, and then another vertex V is in that other top clique. So if U and V are non-adjacent, they're one of these two pairs, like this. If you add up their degrees, they come to exactly k minus 1 in this case. So you're not going to get the closure is complete because it is itself its own closure, because there would be no non-adjacent vertices that you would add edges to. And if you look at the number of complete vertices, m plus 1, it's less than the calculated t-value. So you're not going to get a closure result that implies this graph is C-tough. But I don't have the steps written out. This graph is constructed to satisfy the conditions of the best monotone theorem when C equals 2. So here's an example of a property saying that it's too tough, where one of those corresponding closure results will not give us the too tough result, but the best monotone theorem does. The best monotone theorem in this case casted the larger net. And then tenacity, which is a slight modification of toughness. You're just taking in the numerator and you're adding in the number of vertices in a largest component after you remove the cut set. And then you're taking the minimum over those ratios. And then a graph is C tenacious if its tenacity is at least C. So here we define, in this talk, the tenacity of a complete graph on n vertices to be n. So here's Same graph as before for the toughness, which was 1, but here the tenacity is 2 because you're adding in a size here, the size of a largest component, which is 2. So you're getting 2 for that tenacity. So for the property of being C tenacious, there's a recent result here. I've got this ceiling would guarantee that if you have this stability value, right, that's the stability needed for C tenacious. This is the T value, the minimum number of complete vertices that would imply it's C tenacious. And the best monotone theorem is a simple single inequality that you can check. But closure, again, is not stronger than best monotone. So with these numerical values in place for n, c is 2, k, and t, so everything is calculated. T here is calculated, k is calculated based on n and this graph. So we're taking a clique on n plus 1 vertices, complete join, a similar construction, right? And then any pair of isolated vertices, uv, has to be as indicated here. So if you take the sum of their degrees, you get exactly k minus 1. And it's its own closure. It's not complete. And the number of complete vertices is m plus 1, which is less than the computed t value in this instance. So you're not going to get the 2 tenacious by closure. But you do get it by the best monotone condition. Okay? And in the time I have remaining, this is the last example. So basically, I started going through and saying, with these more recent results, can I use the closure theorem to prove the best monotone theorem? And I kept hitting a wall. It never worked. So it wasn't working because it didn't imply the best monotone conditions, unfortunately. So binding number takes a ratio by looking at non-empty vertex sets whose neighbor set is not the entire graph. So a neighbor set is all the vertices that are adjacent to at least one vertex in X. And that can't be the entire vertex set. So you take the ratio of the number of neighbors over the number of vertices in the set under consideration. The minimum is the binding number. A graph is B binding if the binding number is at least B. Okay, here's a graph. The bow tie graph here has binding number 4/3. The circled vertices are the vertices in X. And then the neighbors are the 2 circled vertices on the left, the middle vertex, and the bottom vertex on the right. The top one on the right is in X, but not adjacent to someone in X. So it's not in there. So you get 4/3, and that's the smallest ratio. So a recent result is for stability, B binding is the maximum of checking these ratios depending on N and B. The T value needed is this here. Best monotone degree condition theorem for B at least 1. There is a corresponding theorem for B between 0 and 1, but I'm not going to refer to it here. But here's an example. This was part of my thesis, so this whole thing comes full circle, where if these conditions are in place, then this is the best monotone degree condition theorem for B binding. And closure, again, is not stronger than best monotone. So with n equal to 6, B equal to 2, we can compute k is 9m minus 1, t is 4m. And then similar graph, except you have an edge in that union that you're joining the bottom clique, 3m vertices up to that disjoint union. You have an edge instead of just an isolate, and then another clique. So any pair of non-adjacent would have to be in that edge or in that top clique. And then you add up their corresponding degrees, exactly k minus 1. Your closure is the graph itself, not complete, and it has 3m complete vertices, which is less than 4m, but it's constructed and it does satisfy the best monotone conditions for B equal to 2. So this was interesting in that, can we, for future work, in previous examples, we showed that the closure conditions are not stronger than the best monotone conditions. It is also true that the best monotone conditions are not stronger than the closure conditions. I didn't show the examples where you get the property of, say, 2 binding from the closure result, but not the best monotone result. So neither one casts a larger net than the other. So are there examples of best monotone theorems that are in fact stronger than the respective closure conditions? So either of those 2 closure results, can you get that the best monotone theorem casts a larger net than either of those? Or can we prove that that never happens? Because we saw examples at the beginning for Hamiltonicity and connectivity that the closure result casts a larger net than the best monotone theorem. And now we've seen that it could be that neither is better than the other. But is it ever true that your best monotone theorem casts a larger net? I don't think so. I haven't thought too much about it. Can we prove that you can never have the best monotone theorem beat a closure result? Can we then identify why for certain properties the closure conditions are stronger, but for others it's not? Okay. Like for Hamiltonicity and K connected, what made them special so that the closure result beat the best monotone theorem? Maybe it's because they're integer statements, like Hamiltonicity is a binary statement, 0, 1, no or yes. Connectivity is an integer statement. Binding number, B binding, T tough, T tenacious are all rational numbers. That might have something to do with it. So I'll end here with just the relevant references. A recent survey on best monotone degree conditions, and then the method and graph theory paper that was referenced throughout. And also here is a survey done by one of my co-authors from the best monotone survey paper on closures, a survey paper on closures. Yeah. So that concludes my talk. Thank you.
Questions from the speaker?
Binding number different from the best vertex isoterimatic inequality.
I'm not familiar with what it is you're referencing, so I off the top of my head, I don't have the comparison. I'm sorry.
They seem to be the same.
Okay. Yeah, the binding number was formulated in the 70s, and it was originally called something else.
Anderson.
It's a
Originally done by Anderson.
Well, yeah, Anderson did it, and then there's a separate quantity known as the Anderson number, but Anderson called the binding number by a different name, and I forget what that name was. I usually would know it off the top of my head, but I've forgotten. Yeah, you had a question?
You had a theorem that said if Cn of G, you get it, is Kn for n greater than or equal to 3, G is Hamiltonian.
Yes.
Okay.
Yeah.
I've had many discussions of this with Ron Gould at Emory.
Okay.
Here's my question. If I take this graph G and I can do this closure fairly quickly so I can tell,
Yeah.
Can you show me where that Hamiltonian cycle is?
Oh, can I show you where it comes up? Have you ever looked in the paper by Bondi Clottel? They give some algorithms. I haven't read the details, but I don't know. Did you ever happen to sift through their paper to see if any of those algorithms?
Well over 90% of the sufficiency, Hamiltonian sufficiency conditions,
Okay.
if this is true, then it's Hamiltonian. Don't give you any idea where that cycle is.
Okay.
So that's
Yeah,
the-
so I honestly, I don't think any of the, because I think they were mainly looking at the algorithms for producing the closure. I don't know if at any point that algorithm can determine where the Hamiltonian cycle is. Yeah, I don't know offhand. That's a good question.